to be in agreement with other things we're doing in class. So change tell you what is the x's and those. So in this example, how many denominator roots we have?
3.
3. The denominator roots are the, oh sorry, how many numerator roots?
4.
Sorry, numerator roots. So in this example, how many numerator roots we have? Inside the closed path. 3. So in the example, so number of times is going to be 3 numerator roots inside. How many denominator roots inside? 4, right? So minus 4. Shall we stick to simple? So it's minus 1. What does it mean? It encircles it minus 1 times clockwise. It says counterclockwise. So the result would be that f of s would look something like this. It would encircle the origin 1 time, sorry, 1 time counterclockwise.
So if it's negative, it's counterclockwise.
So that would be minus 1 encircles. Has anyone had this in the class?
No. What if it's 0? No, nothing.
Let's keep it. Okay, do you understand the concept? All right. Now, let's talk. From this follows the Nyquist stability criteria. When is the closed loop system stable? If 1 plus g, whatever, okay, closed loop poles the roots, and when we say roots, that's the same as numerator roots. Because 1 plus GOL also has ratios here. Right? Okay. What is 1 plus GOL? So 1 plus GOL, let's write what 1 plus GOL is. Which is 1 plus GU, GC of S. GU of S is what? It's a ratio of polynomials times e to the, sorry, GU of S is what? It's a ratio of polynomials times e to the minus ds. Right? So that's going to be 1 plus, let's say, numerator over denominator of GOL. Yeah, I write OL. E to the minus ds times the controller transfer function, and the controller transfer function will be a ratio of polynomials. So let's say numerator of controller of GC, denominator of GC. With me? So that's what 1 plus GOL of S is. With me? Got it? Okay? So, the zeros of the numerator, which are the closed loop poles, yes, numerator of this are the closed loop denominator roots, because that's what we have in the denominator of the closed loop transfer function. Remember, all closed loop transfer functions have denominator 1 plus GOL. But that still is a ratio of functions in S. So that has a numerator denominator. Okay? So the closed loop poles are the numerator roots of 1 plus GOL. They're also denominator roots of 1 plus GOL. Okay? So zeros of numerator closed loop poles. Okay? Are the closed loop. Okay? And so these are the roots. Okay, so let me, this is the way I should say. Closed loop poles are the numerator roots the denominator roots are the roots. What's the denominator of this thing, guys?
1 plus BO.
It's the product of DOL times DC. Right? So are the roots of DOL of S times the denominator of the controller transfer function of S. So are we clear? So how would we apply the complex variable result that I discussed here? I can, if I do a mapping of f of s equals 1 plus GOL. So if we do we are going to do a mapping of f of x equals 1 plus GOL as travels the closed curve that is the Nyquist path. Now, here is the nice thing about the Nyquist path curve. It's designed so that it will have inside it every single positive numerator and denominator root of 1 plus GOL. Right? By its design, it has inside it every possible positive real part root and no negative real part root. With me? We'll discuss zero later.
Okay.
Zero real part. When we bring integral action. Okay? So, the result of this would be that. So, oops. Number of zeros, I guess let me do the number of zeros of plus GOL. And what are the zeros of the numerator roots of 1 plus GOL? Which is number of zeros of 1 plus GOL inside the Nyquist path, in other words, with positive real part. Okay? Because any zero of 1 plus GOL with positive real part would be inside the Nyquist path. Wait a minute. By its design, it would have all positive zeros of 1 plus GOL inside. So the number of zeros of 1 plus GOL with positive real part, which is the same as the number of closed loop poles Now, twist it around. Number of numerator roots of f of s will be the number of encirclements plus the number of denominator roots. You see that? Twist that around. It's going to be equal to the number of times 1 plus GOL of s encircles the origin, plus the number of denominator roots of 1 plus GOL with positive real. Let's digest that. So what is the result here? That the number of times you encircle the origin, and let's call that n. Okay? So the equation I wrote on the left is n, which is the number of times you encircle the origin, is equal to the number of numerator roots of f of s. So let's say n numerator minus the number of denominator roots. That's what this is. Another way to write this is the number of numerator roots is equal to n plus n denominator. That's what I wrote up there. I applied that now to 1 plus GOL, taking f equal 1 plus GOL and taking the path to be the Nyquist path. So let me say it one more time.
Yeah.
The Nyquist path is designed so that it's a closed curve that will have inside it every possible numerator and denominator root with positive real part and none that doesn't have positive real part. So the number of numerator and denominator roots inside it are the number of positive real part numerator or denominator roots of that f, of that 1 plus GOL. Okay? Clear? And so, from that complex variables theorem, we have that the number of numerator roots of 1 plus GOL, which are the number of closed loop poles with positive real part, is going to be the number of encirclements of the origin from 1 plus GOL minus plus the number of the denominator positive roots of 1 plus GOL.
What is that n? Is this min? N min of mim?
No. Numerator.
No, the bottom one, the bottom one.
Same thing.
The bottom one on the left?
Yes.
Oh, you're just rewriting it? Oh.
And capital means encirclements of origin. Number of numerator roots inside minus number of denominator roots inside.
Okay.
So the number of numerator roots inside is the number of encirclements plus the number of the denominator roots inside.
case of P control, would the number of denominator roots be the number of open holes?
I will go there in just a second. You're thinking ahead. The answer is, I'll address that just right. Okay. So, the number n numerator would be the number of positive closed loop poles, which should be 0 to have closed loop stability, right? What about n? We could do the plot, take a string, and follow and see how many times in a circle minus 1 zero. What about the number of denominators inside? What is the denominator of 1 plus GOL? It's the product of the denominator of GOL, of GU, sorry, denominator of GU. Oh, damn it, I missed my notation. This would have been U. Please change the notation here. This is supposed to be U. This is the GU that I wrote. So change that to NU DU. And make that DU. Sorry. This is GU, which is numerator of GU divided by denominator of GU e to the minus ds, and this is the control. So please change the OL to U. Get one okay? Let's change it to U. And so here also should be du dc. So, number of denominator roots of 1 plus GOL is equal to number of roots of du dc. Actually, specifically make number of positive the number of positive real part denominator roots of 1 plus GOL is equal to the number of positive roots of du dc. Everybody against that? Okay? 1 plus GOL is 1 plus du dc. GU has numerator NU, denominator du, e to the minus ds. GC has NC over dc. Okay? Make common denominator, and the common denominator is du dc. Andrea, question? Are you with me, I hope? Okay, so what do we have? We have 1 plus GU and numerator u over denominator u e to the minus ds times numerator controller, denominator controller. Okay? So that can be rewritten as du dc plus nu nc e to the minus ds divided by du dc. So the denominator roots of 1 plus GOL are the roots of du dc. And therefore the positive denominator roots of 1 plus GOL are the positive roots of du dc. Now, we have seen all the controller transfer functions. What are the controllers? Well, it's all been said, P is 1, so I can have GC can be KC for P, tau I is KC of tau IS plus 1 over S, and ideal PID would be tau IS plus 1 plus tau D S squared over tau I, over tau IS. Does any of them have a denominator root with positive real part? No. Otherwise, my control would have been unstable.